So I want to discuss our understanding of pressure with an actual example of when we use this quite often. This is actually with hydraulic lifts. So in auto mechanic shops, they use this a lot. You'll hear the term PSI. It is a unit measuring pound per square inch. There's a conversion to it from pascals. That's the unit we're primarily going to be working with. I'm not a big fan of the pound or inch scale system. I'm more of a fan of the metric scale system. That's the scientist in me. You'll see more use of PSI units in engineering because we live in the United States of America. They use not the metric system. Anyway, so that's what it is, but that's kind of where the term PSI comes from. But essentially what a hydraulic lift is it uses the concept of pressure. So pressure as defined as the force over a squared area. So this is an area. We can kind of use a fluid, so an incompressible fluid like water, for example. I can't compress water, and if I just by changing the square area, so the surface area, I can increase or decrease the force required. The pressure remains constant. So, for example, we're going to use an example of a hydraulic lift trying to lift a car. Car's mass is close to about 2,000 kilograms. They're heavy, right? And if you were to go and just try and lift a car, I mean, just to put it in context, the gravitational force of this car is the mass times its gravity. That's going to be the 2,000 kilograms times 9.81 meters per second squared, which is 19,620 newtons. It's heavy, right? Can't lift a car. We're not The Rock. Or who else can lift a car? Maybe Arnold Schwarzenegger back in his prime? I have no idea. Anyway, we're not The Rock. We can't lift a car. So we can use our mighty physics brains, though, to lift the car for us or making it easier to lift the car, right? So the way that this works is the car can be sitting on top of a hydraulic lift, and we'll say that these are circular cross-sectional areas, so circular tubes. And the radius of the area over which the car sits has, or the radius of the circle over which the car sits, we'll say 0.6 meters. All right. And then we're going to say where we apply it under the hydraulic lift portion, that has, so this will be R2. The radius where we're going to apply the force we'll call R1. That has a radius of 3 centimeters, which we know would be 0.03 meters. So much smaller. And that's actually what we want. We want it to be much smaller. The way we would set up this equation then is that the pressure at one end has to equal the pressure at the other end. So where we're applying the force, that's the end we're calling the one end. This is where we're calling the two end. So then if I expand this, that means the force in newtons, so this is newtons. I wrote N for newtons. I don't know why I did that. I wrote the unit. It should be F for force. I'm sorry about that. The force that we're applying then, because that's the force on the left side, divided by the cross-sectional area. So we'll call this the area at the one side, which we'll figure out in a second. We're going to use the area of a circle, which is pi r squared. That needs to equal the force at the second side. Well, what force is happening at the second side? Well, assuming the car's not moving, the pressure from the hydraulic lift needs to perfectly counter gravity. So the applied force of the hydraulic lift needs to equal the gravitational force, which we have already calculated because we know the mass of the car, we know how heavy it's going to be over its much larger cross-sectional area. So if I want to figure out how much force is required to lift this from the small hydraulic side, I can multiply A1 to both sides of my equation. So I get the applied force. That's going to be what I push or how much I push or how much pressure I need to apply. That's going to equal gravitational force divided by the cross-sectional area at 2, A2 times the cross-sectional area at 1. So we can expand this essentially. So the applied force we need to make the car lift. This is going to be gravitational force. Well, what is the cross-sectional area below the car? That's the circular area underneath the car. That's pi r squared. The radius It's much larger under the car. So we see how that affects the area. So it's pi, this is going to be R2 squared, times the area of the first one. So this is going to be pi R1 squared. We actually notice pi's cancel. Don't need to consider those. I can then rewrite the equation like the force applied. That's going to equal gravitational force times the first radius squared divided by the second radius squared. And I can plug this in my calculator. I get 19,620 newtons. That's what we already calculated. The radius of the first one, I'm going to keep these all in meters. The reason for that is if I want to figure out applied force, I want my end result to be in newtons. So long as the units are the same, everything should work out. My first radius is the 0.03 meters. That's squared. That will affect our number. Divided by the second radius of 0.6 meters squared. When I calculate this, I get applied force required to lift this car of 49.05 newtons. Way less than the 19,620 newtons, right? Significantly less. In fact, it is about 0.25% the force required to lift that car. So we see hydraulic lifts are very useful in terms of lifting heavy things. And so that's just a little example of how we can use pressure to our benefit.